In this presentation we will introduce more fundamental quantities in mechanics such as momentum, work, power and energy, allowing us to provide a complete description of motion in dynamics. The content of this presentation is the following. We will start with the definition of the momentum of a point mass, which is a dynamic quantity characterizing its state of motion. Then we introduce another quantity of a point mass called impulse related to short-time effects changing its state of motion. The third quantity which we will define here is the work done on a point mass by a given force. First we introduce work in a special case, when the point mass moves along a line while a constant force is exerted on it, and extend the definition for a motion along a general trajectory and an arbitrary force. As an illustration, we will also present several examples where we determine the work done on the point-like body by different kinds of forces, that is, we derive the work for different laws of force. In order to characterize the time rate of doing work, we define the concept of power for a constant force and generalize it. We express it in terms of the force doing the work as well. Based on the concept of work, we will able to introduce the energy of a point-like body, and we also define two types of energy: the potential energy of a body related to its position, and the kinetic energy of a body related to its state of motion. Then we prove the work-energy theorem for a point mass, and formulate the law of conservation of mechanical energy, which is valid for both point masses and systems of bodies. We will generalize the definition of potential energy based on the work done by conservative forces as well. The definition allows us to derive any conservative force acting on a body if its potential energy is given, and conversely, it also provides a criterion to determine whether a force is conservative or not. We elucidate the role of the reference state in the definition of potential energy, and we finish the presentation with some examples related to the conservation of mechanical energy. The application of the fundamental equation of dynamics and the law of interaction are basically enough to study not only the motion of an individual point mass but also the dynamics of more general mechanical systems. However, the study of motion can be substantially simplified by introducing proper concepts in physics, such as momentum, energy and work. We can derive theorems related to these quantities from the fundamental equation and the law of interaction, which can facilitate the solution of problems in dynamics. Sometimes we can even obtain enough information on the problems from these theorems without solving the problems themselves. Here we introduce those concepts starting with the quantity called momentum. The momentum p of a point-like body of the mass m and the velocity v is defined by the product of its mass m and its velocity v. The velocity v is measured in a given frame of reference represented at reference point O, where the position vector r describes the instantaneous position of the point mass. Then the momentum p of a point mass is a vector and points in the direction of its velocity v. By definition, the unit of momentum is equal to the unit of mass times the unit of length times the unit of time to -1, and it is given by kilogram meter per second in SI. It also follows from the definition that a body of the mass m and the velocity v has the same momentum as the one of the mass m over 2 and the velocity 2 times v. In other words, a more massive object and the less massive one can have the same momentum if their instantaneous velocities point in the same direction, but the massive object is slower than the less massive one. Since the velocity v of the point mass is defined by the derivative of its position vector r with respect to the time t, the momentum p of a point-like body can be computed from the product of its mass m and the time derivative of its position vector r. In the original formulation of the second law of motion, Newton stated that the change of motion of a body is proportional to the force exerted on the body and it points in the direction along which the force acts. Here the change in the motion must be read as the rate of change of the momentum of the body, that is the derivative of the momentum with respect to time. Newton's second law of motion states that the derivative of the momentum p of a point mass m with respect to the time t is equal to the force F acting on the point mass, that is the time derivative of the product of the mass m and the velocity v of the point mass is given by the force F. In classical mechanics the mass of a body is constant, that is independent of time and motion, and the mass m of in the left-hand side of the second law of motion can be factored out from the derivative. Since the acceleration a of a body is defined by the derivative of its velocity v with respect to time, the second law states that the mass m of the point-like body times its acceleration a is equal to the force F acting on the point mass. This is the original form of the law in which we presented it in the lecture, and now we have two equivalent forms for the second law of motion. In the case of point masses moving at velocities close to the speed of light, for example cosmic rays hitting the atmosphere of the Earth, the second law of motion in terms of momentum holds. However, rockets burning significant amount of fuel during flight represent variable mass systems, and their motion can only be described by applying the second law of motion in terms of acceleration. In the second law of motion, force represents an effect changing the state of motion of a point-like body. If this effect only lasts a short time, for example in the case of pushing, punching or shoving a body or the collision of balls, it is preferable to express the second law of motion in a different form. Let us suppose that a constant force F is exerted on a point mass m for a short time tau, as shown in the graph of its magnitude as a function of the time t. Then the time derivative of the momentum p of the point mass in the second law of motion can be written as the change delta p divided by tau, which is equal to 1 over tau, the difference between the mass m times the velocity v of the point mass at the time tau and the mass m times the velocity v at the initial time 0. The second law states that this difference divided by tau is equal to the constant force F acting on the body over the given interval of time between 0 and tau. Here we have the equation stating that delta p given by the difference of the momentum p of the point mass at the time tau and the initial time 0 is given by tau times the force F, or the mass m times the velocity v of the point mass at the time tau, minus the mass m times the velocity v at the initial time 0 is equal to tau times the force F. In the right-hand side of these equations, we can see the product of the length of the time interval tau and the force F acting over the time interval, which is represented by the area under the curve of the magnitude of the force F. If the application of the force on a body only lasts a short time, then neither the force F nor the time tau is known. However, their product can be determined by measuring the mass and the change in the velocity of the body. Then the product of the force F and the length tau of the time interval over which the force is applied can be defined as a separate quantity. It is called impulse, and denoted by J. Then the second law of motion states that the change in the momentum p of the point mass is equal to the impulse J acting on it. If the force F is not constant but some arbitrary function over the time interval between 0 and tau, then the time interval can be divided into n small subintervals such that the force F can be approximated with a constant value Fi over each interval delta Ti. For each interval delta Ti, the second law of motion can be written as the equation stating that the momentum p at the time Ti plus 1, minus the momentum p at the time Ti, is equal to the average value Fi of the force over the interval times the time delta Ti. Here the total area under the curve of the magnitude of the force over the time interval between 0 and tau is equal to the sum of the individual rectangles over the subintervals. Then the momentum p of the point mass at the time tau minus the momentum p at the initial time 0, or m times the velocity v at the time tau minus m times the velocity v at the initial time 0, can be written as the telescoping sum of the differences between the values of the momentum at the boundaries of the small intervals. In such a sum, subsequent terms cancel each other, leaving only the initial and final terms. As a result, the difference in the left-hand side is equal to the sum of the average Fi of the force over the interval, times the interval delta Ti. By refining the division of the time interval between 0 and tau such that the lengths of the individual intervals delta Ti tend to 0, while the number n of the intervals tends to infinity, we can take the limit of the sum in the right-hand side. This limit is equal to the integral of the force F with respect to the time t from the initial time 0 to the time tau. Now we introduce the time average F bar of the force acting over the time interval between 0 and tau, defined by 1 over tau times the integral of the force F with respect to the time t from the initial time 0 to the time tau. At the same time, we define the quantity impulse J in the general case by the integral of the force F with respect to the time t from the initial time 0 to the time tau. It follows from the definitions that the impulse J acting on a body is equal to the time interval tau times the average force bar F exerted on the body over the time interval. As a result, the second law of motion states that the momentum p at the time tau minus the momentum p at the initial time 0, that is the mass m times the velocity v at the time tau minus the mass m times the velocity v at the initial time 0 is given by tau times the average force F bar, which is equal to the impulse J by definition. Now we can conclude that the difference delta p in the momenta of a point mass at the start and the end of the time interval over which the force F is exerted on the point mass, can be written as the impulse J. In the general case, the change in the momentum p of a point mass is also equal to the impulse changing the state of motion of the point mass. Another important quantity introduced in physics is work. The concept of work in physics goes back to the experience in everyday life and the physiological state of feeling fatigued or exhausted. In the everyday language, work is done, for example, when someone lifts a body or a horse pulls a cart, illustrating that the greater force is applied over a greater distance, the greater work is done. If we discuss these or other similar examples in physics, we talk about the work done on a body by a force applied on it, and adopt the following convention. If a constant force F is applied on a body in the direction of the displacement of the moving body, then the work W done by the force F while the body covers the distance s is measured by the product of the magnitude of the force F and the distance s. It follows from this definition that work only depends on the applied force F and the distance s, whereas it is independent of the mass of the body or the time interval over which the force is exerted on the body. For example, we can lift a body with a force F equal to or greater than its weight g. In the first case, the body moves upward at a constant speed after its initial acceleration if it was at rest, that is, its acceleration vanishes, while in the second case it performs a uniformly accelerated motion upward, that is, it has a non-zero acceleration. However, with regard to the work done on the body by the force F, it does not make difference whether the body has changed its state of motion or not. Since the unit of force is given by the unit of mass, times the unit of length, times the unit of time to -2, the unit of work is equal to the unit of mass, times the unit of length to 2, times the unit of time to -2. If we use SI units, then we measure work in kilogram meter squared per second squared. This unit is also called joule, named after the English physicist James Prescott Joule. Then 1 joule is equal to 1 Newton meter or 1 kilogram meter squared per second squared. In other words, 1 joule is defined as the amount of work done when a force of 1 Newton is exerted through a distance of 1 meter. In the general case, the force acting on a body does not necessarily point in the direction of the body's motion. Furthermore, the direction of the force exerted on a body can also change in time, or the body can also move along a curved path. In order to generalize the definition of work, let us consider a small displacement of the point mass along its trajectory, which is described by the vector delta s. The vector points in the direction of the displacement and its length gives the distance measured along the displacement. Here the angle alpha is measured between the displacement vector delta s and the force F acting on the point mass. Then the work delta W done on the point mass by the force F is equal to the projection of the force F onto the direction of the displacement times the length of the displacement delta s. The projection of the force F can be written as the magnitude of the force F times the cosine of the angle alpha. That is, the work delta W is equal to the scalar product of the force F and the displacement vector delta s. It follows from this expression that the work done by the force is 0, if the force is perpendicular to the displacement of the body. It is convenient to apply some coordinate system attached to a frame of reference, when we compute the work done by the force F exerted through the distance delta s. In a Cartesian coordinate system, the components of the force F is given by Fx, Fy and Fz, whereas the displacement vector delta s has the components delta x, delta y and delta z. Then the scalar product in the expression obtained for the work W can be written as Fx times delta x, plus Fy times delta y, plus Fz times delta z. We will use the formula derived for the work W for the general case, where a point mass travels along a curved path described by the curve C between the points A and B, and the force F exerted on the point mass changes along the curve. First, we approximate the trajectory of the point mass by breaking up the curve C between the points A and B into a series of n displacements, where the first displacement delta S1 starts at the point A, and the last displacement delta Sn ends at the point B. Then we project the instantaneous force Fi at the midpoint of each displacement delta Si into the direction of the displacement, and we calculate the approximate work delta Wi done by the force F through the displacement as the product of the projection of the force Fi and the length of the displacement delta Si. Now we can approximate the total work done along the curve by the sum of each individual work delta Wi done along the series of displacements, that is, the total work is equal to the sum of the projection of the force Fi times the length of the displacement delta Si for each displacement in the series. By refining the division of the curve C between the points A and B such that the lengths of the individual displacements delta Si tend to 0, while the number n of the displacements tends to infinity, we can take the limit of the sum in the right-hand side. The limit is equal to the integral of the projection of the force F onto the tangent to the curve C with respect to the arc length S from the point A to the point B. The projection of the force F in the integrand can be written as the magnitude of the instantaneous force F times the cosine of the angle alpha between the force and the tangent to the curve C. As a result, we can formulate the definition of work in a general case stating that the work W done on a point-like body by the force F along the curve C between the points A and B is equal to the line integral of the force F along the curve C between the points A and B. If we want to calculate the line integral for the work done by the force F along the curve C, we need to express both the components of the force and the curve as functions of the Cartesian coordinates. The integral with respect to the Cartesian coordinates over the curve C can also be written as a parametric integral over an interval by expressing the coordinates of the curve C in terms of a parameter, for example the arc length s measured along the curve. Here the x, y and z coordinates of the curve are written as the functions f, g and h of the arc length s. Then the differentials of the Cartesian coordinates are given by the derivatives of the functions f, g and h with respect to the arc length s, times the differential of the arc length s. By substituting these equations into the integral, we can transform it into a parametric integral with respect to the arc length s over an interval between the points a and b. We supplement the definition of the work W the following convention. If the work W is done by the force F, then minus W denotes the work done against the force F. We use this expression when the work done by the force is negative, that is the work done against the force F, for example by a force minus F acting on the same body is positive. The line integral over the trajectory of a point mass is negative if the angle between the tangent to the trajectory, and the force F acting on the body is obtuse angle over the whole trajectory. Then the work done by the force F is negative. However, the work done by the force minus F is positive since the angle between the force and the tangent to the trajectory is an acute angle. We can interpret this fact as the body does the work against the force F acting on it, or the work is done on the body by the force minus F. We can also prove the following theorem. If a system of forces F1, F2, ellipsis, Fn is exerted on a point mass, then the work done by their net force F is the algebraic sum of the works done by the individual forces F1, F2, ellipsis, Fn, respectively. This theorem follows from the consideration that the total work delta W done by the net force F through the displacement delta S is equal to the scalar product of the force F and the displacement vector delta S, where the net force F is the vector sum of the forces F1, F2, ellipsis, Fn. Since we can remove the bracket, we can split the scalar product and write the work W as the sum of the scalar products of the individual forces with the displacement vector delta S. Each term in the right-hand side represents the work done on the point mass by the individual forces, that is the work done by the net force is the sum of the work W1, W2, ellipsis, Wn done by the system of forces. This proves the theorem. Let us look at some examples of calculating the work done by different forces. In the first example we determine the work done by the gravitational force and the work done when a body is lifted. If a body has the mass m, then its weight G is given by its mass m times the gravitational acceleration g. By applying a constant force F greater than the weight G, we are able to lift the body through a given height h, and the work W done by the force F is equal to the magnitude of the force F times the height h. At the same time, the work W' done by the gravitational force is given by minus the mass m times the magnitude of the gravitational acceleration g, since the angle between the direction of the displacement of the body and the gravitational force acting on the body is equal to 180 degrees. If the body is lifted very slowly at a negligible speed, then the net force acting on the body is almost zero, and the difference between the magnitudes of the force F and the weight G is also negligible. In this case, all the work W is done by the force F against the gravitational force, that is the force F is just great enough to overcome gravity. In the other case, we lift the body by applying a force F greater than the weight of the body. Then the magnitude of the acceleration a of the moving body can be obtained from the second law of motion stating that it is equal to the magnitude of the net force acting on the body divided by its mass m. Since the magnitude of the net force is given by the magnitude of the force F minus the magnitude of the weight G of the body, this expression is equal to the difference of the magnitude of the force F and the mass m times the magnitude of the gravitational acceleration g, divided by the mass m. Here the work W done by the force F is greater than the work W' done by the gravitational force, and not all the work W is done against gravity. The part given by W minus W', that is the magnitude of the force F times the height h minus the mass m times the magnitude of the gravitational acceleration g times the height h increases the speed of the body. However, no matter how much force is applied to lift the body, the work W done against gravity when a body of the mass m is lifted through the height h is always equal to minus the work W' done by the gravitational force, that is the mass m times the magnitude of the gravitational acceleration g times the height h. In this case, the work W' done by the gravitational force is minus m times g times h, whereas m times s times h for a body descending through the height. Let us consider 2 points A and B, where the point A is on the ground and the point B is at the height h. We can move a body of the mass m from the point A to the point B in different ways. For example, first we pull the body along the ground to the point C, them lifted from the point C to the point B. Then the work done against gravity is 0 along the path between the points A and C, since the gravitational force is perpendicular to the path. Therefore, the total work done against gravity is equal to the mass m times the magnitude of the gravitational acceleration g times the height h. We obtain the same result if we move the body from the point A to the point B along the path represented by the steps drawn between the 2 points. In this case, the work done against gravity is 0 along the horizontal segments of the path, whereas the works done along the vertical segments add up to the total work m times g times h. We can choose any arbitrary curve C connecting the points A and B along which the body is moved between the 2 points. The work done against gravity still remains the same. This is evident from the fact that we can also approximate the curve with steps, where the lengths of the segments forming the steps tend to 0 while the number of the steps tend to infinity. Then we can conclude that when a body is brought from one point to another one along an arbitrary path, the work done by or against the gravitational force only depends on the relative positions of the points, and is independent of the path. Let us choose another curve C' connecting the points A and B. Now we bring the body from the point A to the point B along the curve C, then we bring it back to the point A along the curve C'. Based on the conclusion, the total work done along the 2 curves forming a closed loop is just the sum of the 2 works done along the 2 curves. The work done on the ascending body by the gravitational force is equal to minus m times g times h, whereas the work done on the descending body is equal to m times g times h. As a result, the total work done along the closed loop vanishes. Then our final conclusion is that the work done by or against the gravitational force along any closed curve is 0. In the next examples we determine the work done against frictional and elastic forces. When we studied sliding with friction on a horizontal surface, we saw that in order to maintain the motion of a body sliding at a constant velocity, a force F has to be applied which overcomes the frictional force F sub F between the body and the contact surface. Therefore the force F applied on the body is equal to minus the frictional force F sub F. The work W done by the force F while the body covers the distance s over the surface is given by the magnitude of the force F times the displacement s. Here the magnitude of the force F is equal to the 1 of the frictional force F sub F, and Coulomb's law of friction states that the magnitude of the frictional force is given by the coefficient of the sliding friction mu times the magnitude of the force N normal to the contact surface. Then the work done by the force F is equal to the frictional coefficient mu times the magnitude of the force N times the displacement s. This formula holds for sliding along an arbitrary path over the surface, provided the magnitude of the frictional force F sub F is constant along the path. If the path is approximated with a series of displacements denoted by delta Si, with the index I running from 1 to n, then the force F pointing in the direction of the displacement delta Si can be considered constant over each segment. Therefore, the frictional work done along the curve can be approximated by the magnitude of the frictional force F sub F times the sum of the series of the displacement delta Si. If we refine the series of the displacements approximating the curve such that the lengths of each displacement delta Si tend to 0 while the number n of the displacements tends to infinity, then we obtain the arc length s measured along the curve. As a result, the work W done against the frictional force is equal to the magnitude of the frictional force times the arc length measured along the path of the motion, and this work is always positive as opposed to the work done by the gravitational force. We can also conclude that the work done on the body brought along a curve over a surface depends not only on the initial and the final points of the motion but also the curve itself. In other words, the work done against the frictional force along a closed curve does not vanish. In the other example we determine the work done against elastic forces. When we studied Hooke's law we saw the restoring force in elastic deformation is given by minus the spring constant k times the linear displacement x produced by the deformation. If we stretch a spring attached to the wall then we need to overcome the force F in the direction of the spring's axis by applying the force minus F, which is equal to the spring constant k of the spring times the displacement x measuring the stretch of the spring due to the force. Although the force applied on the spring points in the direction of the spring's axis, its magnitude depends on the displacement. Then the work W done against the elastic force of the spring is given by the integral of the magnitude of the elastic force F with respect to the displacement x from 0 to the maximum displacement x0. Since the magnitude of the elastic force F is equal to the spring constant k times the displacement x, the work W is given by 1 over 2 times the spring constant k times the square of the maximum displacement x0. In other words, the work done against the elastic force of the spring is proportional to the square of the displacement of the string, where the proportionality constant is the spring constant. The graphic representation of the work W can be seen in this figure, where the magnitude of the force F applied on the string is plotted as a function of the displacement x. The magnitude of the force is equal to k times x0 at the maximum value x0 of the displacement, and the shaded area gives the work W done against the elastic force of the spring. Finally, we consider more general examples related to work, such as the work done on bodies during uniform acceleration or the work done by constrained forces. The previous examples demonstrated that the force F applied to lift bodies or overcome frictional force moves the body without accelerating it due to the force minus F also acting on the body. If the net force F acting on the body is not zero, then it will accelerate the body, and we can compute the work W done by the force F while the moving body covers the displacement s. We consider a special case where the force F is constant and the initial velocity of the body is zero. The second law of motion states that the constant force F exerted on the body will set the body in motion with a uniform acceleration a in the direction of the force, which is given by the force F divided by the mass m of the body. Then the body covers the distance s in the time interval between 0 and t, where s is given by 1/2 times the magnitude of the acceleration a times the square of the time t. By definition, the work W is the magnitude of the force F times the displacement s of the body. Here we can apply the second law of motion and write the magnitude of the force as the mass m of the body times the magnitude of the acceleration a. If we substitute the expression given for the distance s into the right-hand side, then we can write the work as 1/2 times the mass m, times the square of a times t. Since the instantaneous speed v of the body at the time t is equal to the magnitude of the acceleration a times the time t, the work W done by the force F accelerating the body can be expressed as 1/2 times the mass m of the body times the square of its speed v. This result shows that the work done by the force F accelerating the body from rest to the velocity v only depends on the mass m and the final speed v of the body. The force and the displacement are arbitrary parameters and only their product is fixed for a given amount of work W, and it can be shown that the formula obtained the work holds for motions along a curved path as well. We can use this result in the computation of the work done when we lift a body through the height h by applying a constant force F with a magnitude greater than the weight G of the body. The work W done on the body by the force F is equal to the magnitude of the force F times the height h. Since the second law of motion states that the net force acting on the body is equal to the force F minus the weight G, we can express the magnitude of the force F as the mass m of the body times the sum of the magnitudes of the acceleration a of the body and the gravitational acceleration g. By removing the bracket, we see that the work W has two parts. The term m times a times h is the part representing the work related to the acceleration of the body, whereas the part m times g times h is the work done against gravity. The first term can be expressed in the same form as the one above, and we can conclude that the work done on a body at rest by a force F while it is lifted through the height h is equal to 1/2 times the mass m of the body times the square of the speed v of the body at the height h, plus the mass m times the magnitude of the gravitational acceleration g times the height h. We also need to mention the other general case of the work done by constrained forces. When we studied constrained motion of a point-like body, we saw that the body moves along a given curve or over a given surface representing some geometric constraint imposed on the motion. The constrained force F' keeping the moving body on its path is normally perpendicular to the instantaneous displacement delta s of the body along the path. Therefore, the scalar product of the constrained force F' and the displacement s vanishes in the work W done by the constrained force, or generally, the line integral of the force F' with respect to the arc length s along the curve C representing a given constraint vanishes. Then we can conclude that the work done by constrained forces is always zero. We have seen that the work done by a force through a distance depends on the force and the distance, whereas it is independent of the time interval over which the force is exerted on the body. However, it is oftentimes not only important to determine the work done by a force, but also how long it takes to do that work. In order to describe the rate of the work done by a given force with respect to time, we will introduce a new quantity called power and denoted by the letter p. We define the average power P of a given force as the ratio of the work W done by the force to the time t required to complete the work. In other words, power is equal to the work done in unit time. Since the unit of work is given by the product of the unit of mass, the unit of length to 2, and the unit of time to -2, the unit of power is equal to the unit of mass times the unit of length to 2 times the unit of time to -3. In SI units, power is given in kilogram meter squared per second cubed, which is called watt with the abbreviation W, and it was named after James Watt. Then we can write that 1 watt is equal to 1 joule per second. Based on the definition of the average power, we can introduce the power P of a given force acting on a body as the derivative of the work W done by the force with respect to the time t. The definition of the average power also helps us to express the power P of the force F performing the work delta W on a body over a small time interval delta t, if we substitute the scalar product of the force F and the displacement delta S covered by the body over the time interval delta t into the work delta W. Then the instantaneous power P of the force F over the time interval delta t is given by the scalar product of the force F and the ratio of the displacement vector delta S to the time delta t. By taking the limit of this expression as delta t tends to 0, we can write the ratio as the derivative of the displacement delta S with respect to the time t, which is equal to the instantaneous velocity v of the body. As a result, the instantaneous power P of the force F is equal to the scalar product of the force F acting on the body and the velocity v of the body. This formula also holds for the work W done by the force F along a given curve C between 2 points A and B, which is given by the line integral of the force F with respect to the arc length S over the curve C between the points A and B. The line integral can be expressed as an integral with respect to the time t over a time interval with the boundaries ta and tb representing the time measured when the body is at the points A and B. Here the derivative of the arc length with respect to the time t is the Jacobian of the transformation applied to the integral, which is the instantaneous velocity of the body moving along the curve C. Then the work W done on a body by the force F along the curve C between the points A and B is equal to the integral of the scalar product of the force F and the velocity v of the body with respect to the time t over the time interval between ta and tb. This expression can be inserted into the definition of the power P, which is equal to the derivative of the integral with respect to the time t. By applying the fundamental theorem of calculus, we can write the right-hand side of the equation as the scalar product of the force F and the velocity v. As a result, the formula stating that the instantaneous power P of the force F exerted on a body is equal to the scalar product of the force F and the instantaneous velocity v of the body also holds in the general case. If the second law of motion is substituted into this expression obtained for power, then the power P of a force F acting on the body of mass m can be expressed as the mass m times the scalar product of the body's acceleration a and its velocity v. This result also shows that the power of the force exerted on a body vanishes if the instantaneous velocity and acceleration of the body are perpendicular to each other. We have already seen that the work always vanishes in the case of constrained motion, and this formula obtained for the power, that is the rate of change of work, is also a consequence of this fact. For example, if a ball is attached to a string and whirled in a circle by hand, it will perform uniform circular motion, where the centripetal force F points towards the center of the circular path of the body, and so does its centripetal acceleration a. Here the acceleration of the body is always perpendicular to its instantaneous velocity v, which is tangent to the circle. Therefore both the work done by the centripetal force and its power vanish during the motion. In the discussion on the work done by or against gravitational force, we saw that if we lift a body through a given height then the body is able to do work. For example, if the body is attached to a string passing through a fixed pulley, then it can also lift and accelerate another body attached to the other end of the string, or move it over a surface of a ramp overcoming friction. A stretched spring is also able to do work if it is released by accelerating the body attached to its free end. If we push a cart on a table, then it will able to coast up a ramp to and reach a given height, or compress a spring with one end fixed. In these examples, we can see that the lifted body, the stretched spring and the traveling cart are capable to do work, that is, these bodies have the capacity of doing work against gravitational, frictional and elastic forces. Then we have the following general statement. If a body or a system of bodies in a given state has the capacity for doing work under certain conditions, we say that the body or the system has energy. The energy E of a given body or system is measured by the work done by the body or the system when it is brought from the state A into another reference state A0. We can choose an arbitrary state as the reference state A0 so that all possible states of the body or the system could be compared with it. In other words, the energy of the body or the system is measured by the work done against the forces acting on the body or the system while is it brought from the state A to the reference state A0. Therefore energy is a quantity which has the same nature as work, and its unit is the same. If we use SI units, then energy measured in joule. When we studied the concept of work in physics, we saw that any object at a given height above ground is able to do work because of its position at the given altitude with respect to the level of the ground. Similarly, the different parts of a stretched or compressed spring also have the capability of doing work due to their relative positions with respect to each other. In these or similar cases we can talk about the potential energy of the given body or system. If a body of mass m at the height h above ground is at rest, we can say that the body is in a state A. Here we choose the state where the body is at rest on the ground as its reference state A0. Then we measure the potential energy of a body at the height h above ground, that is in the state A, by the work which is done by the body when it falls from the height h to the ground, entering the reference state A0 from its initial state A. We can determine this work as follows. When a body descends from the height h to the ground, it can lift another body attached to the descending one with a string passing through a fixed pulley with a negligible mass, provided the other body has the same weight and the bodies were set in motion by applying a slight push. Therefore, the body does the work by lifting the other body from the ground to the height h, that is bringing it from the state A0 to the state A. This work is given by the mass m, times the magnitude of the gravitational acceleration g, times the height h, which is called the potential energy of the body. Then the potential energy of a body of mass m at the height h above ground is equal to m times g times h. Since the reference state used to define the potential energy of the body is the state of the body at rest on the ground, the height h is measured from the local surface level of Earth. As a result, this choice provides a local definition of potential energy with respect to the surface level of the ground in the lab, where the experiment measuring the potential energy is performed. In the general case, the reference state of a body can be chosen as the state of the body at the average sea level of Earth. Here no reference on the local surface level of the ground is applied, and this choice provides a global definition of potential energy. As already mentioned, a stretched or compressed spring is also able to do work, where the equilibrium state of the spring is chosen as the reference state A0. The potential energy of a stretched spring in the state A with the displacement x0 is measured by the work done when it is stretched by an amount of x0 from its equilibrium length. Since this work is equal to 1 over 2 times the spring constant k times the square of the displacement x0, the potential energy of the spring in the state A with the displacement x0 is also given by 1 over 2 times k times x0 squared. A moving body is also able to do work due to its velocity, representing another form of energy called kinetic energy of the body. We already determined the work done when a body of mass m at rest is accelerated to the speed v, which is equal to 1 over 2 times the mass m times the square of its instantaneous velocity v. Here the reference state A0 of the body is the state when it is at rest. This work can be used to measure the kinetic energy of the body in a state A when it moves at the speed v, that is the kinetic energy of the body is equal to 1 over 2 times m times v squared. The potential energy and the kinetic energy are the two different forms of mechanical energy possessed by an object due to its position or due to its motion. After introducing the kinetic energy of a body or a system, we can determine the relationship between its change and the work done on the body or the system. This relationship is formulated in the work-energy theorem presented here. We have just determined the work W done by a constant force F acting on a point mass m when it is accelerated from rest to a given speed v, and we found that it is equal to 1 over 2 times the mass m times the square of the speed v. This work is done while the point-like body is accelerated over a given distance, and the formula can also be applied to compute the works done when the moving point mass covers the distances s1 and s2. The work W done on the point mass by the force F when it moves through the distance s1 minus s2 is equal to the magnitude of the force F times the distance s1 minus s2, or F times s2 minus F times s1, which is the difference between the works done on the point mass covering the distances s2 and s1 respectively. If we substitute the formula derived for the work into the two terms, we obtain 1 over 2 times the mass m times the square of the velocity v2, minus 1 over 2 times the mass m times the square of the velocity v1. In the result we can identify the quantities measuring the kinetic energy of the point mass when it is accelerated from rest to the speeds v2 and v1 respectively. Now we can formulate the work-energy theorem as follows. The change in the kinetic energy of a point mass m is equal to the work W done by the force F acting on the point mass, that is 1 over 2 times the mass m times the square of the velocity v2, minus 1 over 2 times the mass m times the square of the velocity v1 is equal to the work W. Here the velocities v1 and v2 are the initial and the final velocities of the point mass accelerated by the force F performing the work W. This theorem holds for the general case as well, where the force F is not constant and the point mass m travels along an arbitrary curve C between the points A and B. We can prove the theorem for the general case by calculating the work done when the point mass is only a small displacement along the curve. The infinitesimal work done on the point mass by the force F through the infinitesimal displacement ds along the curve is equal to the scalar product of the force F and the displacement vector ds. Since the instantaneous velocity v of the point mass moving along the curve is defined by the derivative of the displacement s with respect to the time t, the infinitesimal displacement vector ds and its scalar product with the force F can be written as the velocity v times the infinitesimal time interval dt. If we apply the second law of motion expressed in terms of momentum, we can write the force F exerted on the point mass as the derivative of the momentum p of the point mass with respect to the time t. Here the time derivative of the momentum p times the differential dt of the time is equal to the differential dp of the momentum. Because the momentum p of the point mass is defined by its mass m times its velocity v, the scalar product of the force and the displacement vector is given by the mass m times the scalar product of the velocity v and its differential. This result can be substituted into the work W done by the force F along the curve C between the points A and B, which is equal to the line integral of the force F with respect to the arc length S along the curve C between the points A and B. Then we can transform the line integral into the mass m times the integral of the force F with respect to the velocity v along the curve between the velocities v1 and v2 of the point mass measured at the points A and B. If we perform the integration, then we obtain m times the square of the velocity v over 2 evaluated at the lower and upper limits of the integral, which gives 1 over 2 times the mass m times the square of the velocity v2, minus 1 over 2 times the mass m times the square of the velocity v1. This proves the theorem. The work-energy theorem will help us to derive one of the most important laws in mechanics, the law of conservation of mechanical energy. In order to do so, we will apply the theorem for the most general motion of a point mass under the influence of gravity, which is projectile motion. When we studied projectile motion, we proved that the trajectory of the projectile is a parabola. The motion of the point-like projectile along this parabola can be described in a Cartesian coordinate system attached to a frame of reference, where the z-coordinate measures the altitude of the moving projectile. Let us consider two arbitrary points A and B on the parabola with the vertical coordinates z1 and z2, where the instantaneous velocities of the point mass are denoted by v1 and v2. We already determined the work W done by the gravitational force when a body of mass m moves from one point to another one, for example from the point A to the point B. Then the work W is given by minus the mass m times the magnitude of the gravitational acceleration g times the vertical distance of the points A and B, that is z2 minus z1. If we substitute this result into the work-energy theorem, we can write that 1 over 2 times m times v2 squared minus 1 over 2 times m times v1 squared is equal to minus m times g times the difference between z2 and z1. Then we obtain the equation stating that 1 over 2 times the mass m times the square of the velocity v1, plus the mass m times the magnitude of the gravitational acceleration g times the height z1, is equal to 1 over 2 times the mass m times the square of the velocity v2, plus the mass m times the magnitude of the gravitational acceleration g times the height z2. The first terms in both sides of the equation measure the kinetic energy of the projectile at the points A and B respectively. Similarly, the second terms in both sides of the equation measure the potential energy of the projectile at the points A and B. As a result, we can write that the sum of the kinetic energy and the potential energy of the point mass at the point A is equal to the sum of the kinetic energy and the potential energy of the point mass at the point B. Generally speaking, the sum of the kinetic energy and the potential energy of the point mass is the same at every point along its path, that is, the sum remains constant during the motion of the point mass in the gravitational field. As the projectile increases, the decrease in its kinetic energy is equal to the increase in its potential energy. As the projectile falls, the increase in its kinetic energy is equal to the decrease in its potential energy. In other words, the kinetic energy and the potential energy transform into each other in the motion under the influence of gravity. This statement not only holds for gravitational force but also for conservative forces. We call a force conservative force if it does not change in time and the work done by the force along an arbitrary path connecting two points depends only on the positions of the points, but does not depend on the path itself. This definition also shows that the gravity is a conservative force. Now we can formulate the law of conservation of mechanical energy as follows. If the net force F acting on a point mass is a conservative force, then the sum of the kinetic energy and the potential energy, that is the total mechanical energy E of the point mass, is constant. Let us examine the potential energy of a point-like body under the influence of a conservative force. We saw that the work W done on a point mass by the conservative force F along a curve C between two points A and B depends only on these points. In other words, the work W is a unique function of the points A and B, and it is independent of the curve C connecting the 2 points. Let us choose a point P0 such that the curve C does not pass through it. Then the points P0 and A can be connected with an arbitrary curve C1, and the points P0 and B can be connected with another curve C2. Now we can talk about the work which the force F would do if it was exerted on the point mass along the curve C1 or the curve C2. Since the force F is conservative, the work done by the force F along the curve C1 between the points A and P0 is a unique function of the initial and the final points of the curve. Similarly, the work done by the force F along the curve C2 between the points P0 and B is also a unique function of the initial and the final points of the curve. We can consider the work done along the union of the curves C1 and C2 connecting the points A and B as well, which must be the sum of the individual works done along these curves. Then the sum of these works depends only on the points A and B, and it is equal to the work W done by the conservative force F along the curve C between the points A and B. Here the point P0 is an arbitrary point. However, if we fix this point called 0 point, only the points A and B are needed to determine the works done along the curves C1 and C2. If we introduce a 0 point for the conservative force F, then the potential energy of a body at a given point can be measured by the work done on the body by the force when it is brought from the given point into the 0 point. As a result, the potential energy of the point mass at the point A is given by the work done on the point mass while it is brought from the point A into the point P0. The work is equal to minus the work done on the point mass while it is brought from the point P0 to the point A, which is given by minus the line integral of the force F with respect to the arc length along an arbitrary curve connecting the points P0 and A. Obviously, the integral vanishes if the 0 point P0 and the point A are the same, that is the potential energy of the point mass is 0 at the 0 point. Now we can state that a point mass under the influence of a conservative force F has the potential energy at a given point P, which is equal to minus the line integral of the force F with respect to the arc length S along an arbitrary curve connecting the points P0 and P. Here the potential energy is defined with respect to the 0 point P0. We have seen that the work W done on a point mass by the conservative force F along the curve C between the points A and B is equal to the sum of the works done along the curve C1 and C2 connecting the points A and B through the 0 point P0. Here the work done along the curve C1 between the point A and the 0 point P0 defines the potential energy of the point mass at the point A. Since the work done along the curve C2 between the 0 point P0 and the point B is equal to minus the work done in the opposite direction, we can express it as minus the potential energy of the point mass at the point B. As a result, the work W can be written as the potential energy of the point mass at the point A, minus its potential energy at the point B. Then we can state that the work W done on the point mass along an arbitrary curve between the points A and B is given by minus the difference in the potential energy of the point mass measured at the points B and A. In other words, the work done on a point mass by a conservative force is equal to the negative change in the potential energy of the point mass. If the force F is the net force acting on a point-like body, then we can apply the work-energy theorem stating that the change in the kinetic energy of the body between the 2 points A and B is equal to the work done on the body by the force along any path between the 2 points. By substituting the result derived above into the theorem, we can see that the change in the kinetic energy of the point mass is equal to the negative change in its potential energy. After regrouping the terms in the equation, we obtain the law of conservation of mechanical energy. When we proved the work-energy theorem, we did not assume that the force changing the state of the motion of a point-like body is a conservative force. In the computation of the work done by the force, it does not matter whether the line integral of the force with respect to the arc length along a curve depends on the curve or not. Therefore the theorem holds for both conservative forces and non-conservative ones, if they are applied on the point mass. However, the law of conservation of mechanical energy is formulated for such processes where a conservative force is exerted on a point-like body or system of bodies. The generalization of such a law for both conservative and non-conservative forces involves all possible forms of energy, where we can talk about the law of conservation of energy, that is the total energy of a body or a system of bodies. The total energy of a body or a system consists of all forms of energy which are related to all types of forces acting on the body or the system. These forces can be conservative forces such as gravitational, elastic or electrostatic force, and non-conservative forces such as frictional or drag force. In the examples illustrating the energy defined for different phenomena, we will present bodies accelerated by either a conservative force or a non-conservative one. Since we focus on conservative forces, we study the conservative force F acting on a point-like body in the general case, where the force depends on the instantaneous position of the body. Then the force F can be described by a vector function of the position vector r of the point mass with respect to some reference point O representing a frame of reference. It is normally convenient to choose the reference point O as the 0 point P0 for the definition of the potential energy of any point mass accelerated by the force F. The definition of potential energy also shows that the conservative force F determines the potential energy and vice versa. By definition, the line integral of the conservative force F along an arbitrary curve depends only on the endpoints of the integration, and the line integral along a closed curve vanishes identically. In other words, the line integral of the force F with respect to the arc length s along an arbitrary closed curve C0 is equal to 0. Here we can apply Stokes' theorem stating that the line integral of the vector F along the closed curve C0 is given by the surface integral of its curl, that is the cross product of the nabla operator and the vector F over an arbitrary surface S, where the curve C0 is the boundary of the surface. Since this surface integral is identically 0 for the conservative force F and the surface A is arbitrary, the integrand must vanish. That is, the curl of the force F is identically 0. By applying a vector identity stating that the curl of the gradient of any scalar function f vanishes, we can assume that the conservative force F can be written as the gradient of some scalar function f depending on the position vector r. In fact, we can demonstrate that the function f is determined by the potential energy of any point mass moving under the influence of the force F. We define the potential energy of a point-like body accelerated by the force F at the point P by minus the line integral of the force F with respect to the arc length s along an arbitrary curve between the 0 point P0 and the point P. Since the force F is conservative, we can write it as the gradient of the function F. Now we can apply the fundamental theorem of calculus, which gives minus the difference between the function F evaluated at the points P and P0. If the 0 point P0 is fixed, then we obtain minus the function F at the point P plus a constant. As a result, the potential energy of an arbitrary body at the point P is equal to minus the function F plus a constant, where the constant represents the free choice of the 0 point in the definition of potential energy. Then we can conclude that a conservative force F is given by the negative gradient of the potential energy of any point mass moving under the influence of the force. If we attach a Cartesian coordinate system to the frame of reference, the Cartesian components of the force F are equal to minus the partial derivatives of the potential energy with respect to the corresponding coordinates. Conversely, if there exists a scalar function such that the force F is given by the negative gradient of the function, then the force F is conservative, and the function represents the potential energy of an arbitrary point-like body accelerated by the force. Based on this criterion, we can immediately determine whether gravitational force is conservative or not. We already computed the potential energy of a body of mass m at the height h, which is equal to the mass m times the magnitude of the gravitational acceleration g times the height h. If we choose a Cartesian coordinate system with its origin at ground and the z-axis pointing upward, we can write the height h as the z-coordinate of the body's position. We obtain the components of the force F by computing minus the gradient the potential energy of the body, that is its partial derivatives with respect to the corresponding coordinates. Then the force vector has the component 0, 0 and minus m times g. That is, the force F exerted on the body is equal to its mass m times the gravitational acceleration g pointing downward, which is the gravitational force acting on the body. As a result, we demonstrated that the gravity is a conservative force. Of course, this fact is already known for us because we introduced the concept of conservative force based the example of gravity. However, in that case we determined if the force is conservative by checking if the line integral of the gravitational force along a curve depends on the curve. Here we go in the opposite direction. Instead of integrating the force exerted on the body, we compute the gradient of the potential energy of the body to obtain the conservative force acting on it. We can also determine whether the elastic force produced by a spring is conservative or not. We already saw that the potential energy of a spring stretched by an amount of x0 from its equilibrium length is equal to 1 over 2 times the spring constant k times the square of the displacement x0. Let us suppose that the x-axis points in the direction of the displacement and the x-coordinate represents the displacement x0. Then the components of the force F given by minus the partial derivatives of the potential energy with respect to the corresponding coordinates are equal to minus k times x, 0, 0. As a result, the force F is equal to minus the spring constant k times the displacement vector x, which is Hooke's law showing that the elastic force produced by the spring is a conservative force. Both examples illustrate that the energy of a body depends on the choice of the 0 point or the reference state of the body, and different choices result in different values of the energy for a given state. In the case of a point-like body under the influence of gravity, the local definition of its potential energy uses the state of the body at rest on the ground as a reference state A0. If we choose the state of a point mass m at sea level as a reference state, we have a global definition of the potential energy. Then the height h is equal to 0 for a body in the reference state. For a local definition, the potential energy of the point mass at the height h, that is in the state A, is given by m times s times h, minus m times g times h0, where h0 is equal to an arbitrary altitude chosen as reference state. Similarly, if the reference state A0 of a spring is not its equilibrium state but the state in which it is slightly stretched, then the potential energy of the spring stretched by an amount of x0 from its equilibrium length, that is in the state A, is equal to 1 over k times x0 squared, minus 1 over 2 times k times x0 bar squared. Here x0 bar gives the difference between the length of the relaxed spring and the length of the slightly stretched one. Such a choice of the reference state can be done in the case of kinetic energy of a body of mass m at the speed v as well, which is equal to 1 over 2 times m times v squared. If the reference state A0 of a body accelerated by a force is not the state when it is at rest but when it has the velocity v0, then the kinetic energy of the body in the state A is given by 1 over 2 times m times v squared, minus 1 over 2 times m times v0 squared. The fact that the energy of a body or a system of bodies is only defined to within an additive constant due to the arbitrary choice of the 0 point of the energy, has no physical significance. Since only the differences of the same form of energy appear in the work-energy theorem and the law of conservation of energy, the additive constants depending on the choice of reference states cancel out. Let us examine the law of conservation of the mechanical energy in the examples already discussed here. In the first example, we studied the motion of a point-like body under the influence of gravity. We saw that the law of conservation of mechanical energy states that the energy, that is the sum of the kinetic energy and the potential energy of a point mass m accelerated by the gravitational force does not change. That is 1 over 2 times the mass m times the square of the instantaneous speed v of the body, plus the mass m times the magnitude of the gravitational acceleration g times the instantaneous height z of the body's position remains constant during the motion. It is easy to check this statement in the case of free fall where the initial velocity of the point-like body is 0. If the point mass is at rest, then its kinetic energy vanishes and its energy is equal to its potential energy given by its mass m, times the magnitude of the gravitational acceleration g, times the height h describing its initial position. When the falling body covers the distance s given by h minus z, the decrease in its potential energy is equal to m times g times s. When we studied free fall, we demonstrated that the instantaneous speed of a falling object with 0 initial speed is equal to the square root of 2 times the magnitude of the gravitational acceleration g times the distance s covered by the object. If we substitute this expression into the kinetic energy of the point mass, then we obtain 1 over 2 times m, times 2 times m times s, which gives m times g times s. Since the kinetic energy of the point mass is 0 in its initial state, this is equal to the change in its kinetic energy when it covers the distance s. The comparison of the expressions obtained for the change in the two forms of energy shows that the kinetic energy of the point mass vanishes at the height h and its total energy of the point mass is equal to its potential energy. Conversely, when the falling body reaches the ground, its potential energy vanishes and its total energy is equal to its kinetic energy. This relation also shows the fact which we already established: the kinetic energy and the potential energy transform into each other in the motion under the influence of gravity. As a result, the total change in the energy of the falling point mass is 0, that is, its energy is constant during its motion under the influence of gravity. The second example is a point mass attached to a spring, which performs a simple harmonic motion if we stretch the spring and we release it. The energy of the oscillating point mass m, that is the sum of its kinetic energy and its potential energy, is given by 1 over 2 times the mass m times the square of its instantaneous speed v, plus 1 over 2 times the spring constant k times the square of the instantaneous displacement x of the point mass. The law of conservation of mechanical energy states that this sum remains constant during the oscillation. We also saw that the oscillating motion is produced by the elastic force minus the spring constant k times the displacement x, and it can be described the following time-dependent functions. The instantaneous displacement x is given by the amplitude a of the oscillation, times the sine of the angular frequency omega times the time t. The instantaneous speed v is equal to the amplitude a times the angular frequency omega, times cosine omega t. Here the square of the angular frequency omega is given by the ratio of the spring constant k to the mass m. We can use these kinematic variables to express the energy of the oscillating body as a function of time. The kinetic energy of the point-like body can be written as 1 over 2 times m times a squared times omega squared, times the square of cosine omega t. If we insert the expression defining omega squared into the equation, we obtain 1 over 2 times k times a squared times the square of cosine omega t. For the potential energy of the point mass we obtain 1 over 2 times k times a squared, times the square of sine omega t. Then the total energy of a point mass m performing simple harmonic motion is equal to 1 over 2 times the spring constant k times the square of the amplitude a of the oscillation. Here we use the trigonometric identity stating that the square of sine omega t plus the square of cosine omega t is equal to 1. The energy can also be written as 1 over 2 times the mass m times omega squared times a squared. Both forms show that the energy is independent of time and remains constant during the oscillation of the body. Here we can also see how kinetic energy and potential energy transform into each other. The kinematic variables as functions of time show that the total energy of the point mass is equal to its potential energy in the turning points of the oscillation. When the body leaves one of its turning point, its potential energy starts to decrease and transforms into kinetic energy. When the body passes through its equilibrium position, its total energy is equal to its kinetic energy. After leaving the equilibrium position, the body approaches the turning point in the opposite side and its total energy becomes its potential energy there, and so on. Then we conclude the following: in simple harmonic motion the potential energy and the kinetic energy transform into each other periodically. Let us consider two other examples that have already been studied here. The first one is a mathematical pendulum moving under the influence of gravity, where we can demonstrate the periodic transformation of potential energy and kinetic energy into each other, as in the case of the oscillating point mass attached to a spring. Let us suppose that the point mass m representing the bob of the pendulum is held at the point A, that is at the height h with respect to the equilibrium position B, and then released. Since the initial velocity of the point mass is 0, its energy at the point A is equal to its potential energy given by the mass m times the magnitude of the gravitational acceleration g times the height h. When the swinging bob passes through the point B, its total energy is equal to its kinetic energy given by 1 over 2 times the mass m times the square of the velocity v at the point B. Since mechanical energy is conserved for frictionless motion under the influence of gravity, the total energy of the point mass at the point B is still equal to m times g times h. Then we can express the velocity of the pendulum at the point B as the square root of 2 times the magnitude of the gravitational acceleration g times the height h. The formula shows that the pendulum has the same velocity as the bob would have if it had fallen through the height h. If the bob passes through the equilibrium point, then it reaches the other turning point C. The point C is also at the height h, which is due to the fact that kinetic energy vanishes at the point B and the potential energy at the point C must equal to m times g times h. For the same reason, the pendulum will reach the same height, even if we prevent the upper part of the string used for the suspension from swinging towards the turning point C with a rod perpendicular to the plane of the swinging motion. The law of conservation of mechanical energy holds for a pendulum without friction because the force F acting on the bob is the sum of its weight g, which is an unconstrained force, and the constrained force F' exerted on the bob by the string. Since the constrained force F' is always perpendicular to the path of the swinging point mass, it does not produce work and has no contribution to the energy of the pendulum in the law of conservation. This example illustrates the conservation of mechanical energy for a body traveling along a given curve or over a given surface, provided the net force of the unconstrained forces acting on the body is a conservative force. The last example discussed here is frictional motion, for which the law of conservation of mechanical energy does not hold. When we studied a body of mass m sliding down an inclined plane or a ramp with the inclination angle alpha, we proved that the magnitude of the net force F acting on the body is given by the mass m times the magnitude of the gravitational acceleration g, times the difference between sine alpha and mu times cosine alpha, where mu is the frictional coefficient. Since the work-energy theorem holds in the general case, we can write it in the following form for a body sliding down between the point A and B with a zero initial velocity. The change in the kinetic energy given by 1 over 2 times the mass m times the square of the instantaneous velocity v of the body at the point B, is equal to the work given by the magnitude of the force F times the distance s between the points A and B. By substituting the expression obtained for the magnitude of the force into this equation, we obtain m times g times s, times the difference between sine alpha and mu times cosine alpha. If we apply the trigonometric relations describing the geometry of the ramp, we obtain m times g times the height h of the ramp, minus mu times m times g times the horizontal length L of the ramp. The mechanical energy of the body at the point A is given by 1 over 2 times the mass m times the square of the velocity v of the body at the point A, plus m times g times the height h of the point A measured from the level of the point B. Since the initial velocity of the body is 0, its total energy is equal to the mass m times the magnitude of the gravitational acceleration g times the height h. The mechanical energy of the body at the point B is given by 1 over 2 times the mass m times the square of the velocity v of the body at the point B, plus m times g times 0. If we substitute the expression obtained for the kinetic energy in the work-energy theorem into this equation, we can write the mechanical energy at the point B as m times g times the height h, minus mu times m times g times the length L. Then we conclude that the mechanical energy of the body is not conserved but decreased by the frictional coefficient mu times the mass m, times the magnitude of the gravitational acceleration g, times the horizontal distance L between the points A and B. This difference in the energy is transformed into heat by the friction between the contact surfaces. However, we can still talk about the conservation of the total energy including the amount of energy dissipated into heat. In the end of this presentation on the quantities momentum, work, power and energy, let us summarize the main conclusions. First, we define the momentum of a point-like body as the product of its mass and velocity. By applying this definition, we could rephrase the second law of motion in terms of momentum, stating that if a force is exerted on a point mass, then the rate of change of its momentum is equal to the force. Then we introduced another quantity called impulse, which is the product of a constant force acting on a body over a short time interval and the length of that interval. For non-constant forces, we generalize this definition as the integral of the force with respect to the time over the given time interval. By applying this definition, we could express the change in the momentum of a point mass as the impulse acting on it. The third quantity which we defined here was the work done on a point mass by a given force. First, we introduced work in a special case. The work done on a point-like body by a constant force along a straight line was defined as the scalar product of the force and the displacement vector with the length covered by the body while the force was exerted on it. The work done on a point mass by an arbitrary force along a curve over a section of the curve had a more general definition. It was just the line integral of the force with respect to the arc length measured along the curve between the initial and the final points of that section. We also proved that the work done by the net force of a system of forces is the sum of the works done by the individual forces in that system. As an illustration, we also presented several examples where we determined the work done on the point-like body by different kinds of forces. We calculated the work done by or against gravitational force, when an object is raised from the ground to a given height. We saw that it is equal to minus or plus the mass of the object times the magnitude of the gravitational acceleration times the height. We also found that when a body is brought from one point to another one along an arbitrary path, the work done on the body by or against the gravitational force only depends on the relative positions of the points and is independent of the path. In other words, the work done by or against the gravitational force along any closed curve is zero. We called such a type of force conservative force. In the next example, we determine the work done by frictional forces for a body sliding over a surface at a constant velocity. We showed that this work is equal to the product of the coefficient of friction, the magnitude of the normal force acting on the contact surfaces and the displacement of the body. We also saw that the frictional work is always positive, and the work done on a body brought along a curve over a surface depends not only on the initial and the final points but also the curve itself. In other words, the work done against the frictional force along any closed curve is not zero. We also computed the work done by elastic forces, where we applied Hooke's law for the restoring force in elastic deformation. We proved the work done by an elastic force produced in an expanded spring is proportional to the square of the displacement of the spring, where the proportionality constant is the spring constant divided by 2. Another interesting example was the work done by a force accelerating a body, which is equal to 1 over 2 times the mass of the body times the square of its final velocity, where we supposed that the body was at rest in its initial state. In the last example we saw that constrained forces never do work because they are always perpendicular to the displacement of the body which they are exerted on. In order to characterize the time rate of doing work, we define the power of a force doing work. For a constant force, power is the measure of the work done per unit time. In the general case, power is defined as the derivative of the work done by a force with respect to the time. By applying these definitions, we expressed power as the product of the force doing the work and the velocity of the point mass accelerated by the force. Then we were able to introduce the energy of a body as its capacity for doing work. The energy of a point-like body in a given state is the measure of the work done when the body is brought from its state into a reference state. In other words, it is the work done against the forces acting on the body while it is brought from its state into its reference state. We also define two types of energy: the potential energy of a body related to its position, and the kinetic energy of a body related to its state of motion. The potential energy of a body at a given height measured from a reference level, for example from the ground or the average sea level, is equal to the mass of the body times the magnitude of the gravitational acceleration times the height. The kinetic energy of the body with a given instantaneous speed is equal to 1/2 times the mass of the body times the square of the speed, if the body was at rest in the reference state. Based on these quantities introduced here, we could formulate and prove the work-energy theorem for a point-like body, stating that the change in the kinetic energy of the body is equal to the work done on the body by a force accelerating it. We also demonstrated the law of conservation of mechanical energy by analyzing the parabolic motion of a point mass under the influence of the gravitational force, which is a conservative force. The law states that if the force acting on a body is a conservative force, then the sum of the kinetic energy and the potential energy, that is the total mechanical energy of the body, is constant. The law is valid for both point masses and systems of bodies. We generalize the definition of potential energy based on the work done by conservative forces as well. The potential energy of a body at a given point is defined by the work done when it is brought from a zero point into that point. The zero point is a reference point, where the potential energy of the body is chosen to be zero. As a result, the potential energy of the body is given by minus the integral of the conservative force acting on the body over an arbitrary path between the zero point and the position of the body. This definition allows us to derive any conservative force acting on a body as the negative gradient of the body's potential energy. Conversely, a force is conservative if it can be expressed as the negative gradient of a scalar function, which can be interpreted as the potential energy of a body under the influence of the force. We elucidated the role of the reference state in the definition of energy by examining the result of the choice of different reference states or zero points for gravitational and elastic forces and any force accelerating a body. We concluded that energy is only defined to within an additive constant, and only its difference appears in the equations of theorems and laws related to energy. We finished the presentation with some examples related to the conservation of mechanical energy. In the examples of motion under the influence of gravity and of elastic deformation of a spring, we could study how potential energy and kinetic energy transform into each other. In the case of a mathematical pendulum, we established the conservation of mechanical energy as well. Furthermore, we also saw that the constrained force produced in the suspension string does not do work. In the last example, we studied the transformation of energy in frictional motion over a ramp, and we found that the mechanical energy of a body does not conserve since friction dissipates some energy in the form of heat.